This is a video lesson for spring and elastic potential energy. The essential question for this lesson is, how do we define and calculate spring and elastic potential energy? All right, so let's start by looking at an example. So what is the force exerted by and potential energy stored? So force exerted by and potential energy stored in a spring with a spring constant, K, equals 150 Newton meters, that has been compressed 0.1 meters. Okay, so before answering this question, we need to look at a few things first. So first, let's talk about Hooke's law. So Hooke's law is the stretching or compressing a spring requires a force that's proportional to the distance the spring is stretched or compressed. So the mathematical formula for Hooke's law is F sub s is equal to K times X. So notice we have the absolute value of F sub s and the absolute value of X. So K is the spring constant, and that's in the units of Newton per meters. And we have X, which is the deformation of the spring. So that's the distance stretched or compressed, and that's in the units meters. Okay, so we have a diagram here where we see a spring that's being stretched by a force. So the force F of s is stretching the spring and is displacing it this distance x. So Hooke's law is sometimes stated as the spring exerting a restoring force proportional to the deformation. So note that this is equal to the applied force and in the opposite direction. So here's another diagram where we have the stretching of the spring, and we have the force now is being applied in the opposite direction. So this is the restoring force being applied in the opposite direction that the spring is being stretched. So the force of the spring is trying to pull the spring back in the direction that it's being stretched. So that's the restoring force. And the last bit of information we need to know is about elastic potential energy. So work is done on a spring. So the work done on a spring is stored in the spring as potential energy. And the equation for spring potential energy is U sub E, that's the spring potential energy, is equal to 1/2 K. And again, remember K is the spring constant, and X is that displacement or the spring stretching, and that's squared. So we have 1/2 kx squared, and this is really similar to kinetic energy. So the formulas are pretty close. Okay, so now we have all the information we need to be able to answer this question. So first we want to figure out the force. So spring force, again, is equal to K times X. And we want to figure out the potential energy stored. So UE is equal to 1/2 K times X squared. So first let's figure out the force. So our K is equal to 150 newtons per meter, and our X is 0.1 meters. So multiply those together, and we end up with a spring force of 15 newtons. All right, so the restoring force on the spring is 15 newtons. Now let's look at our potential spring energy. So we have 1/2, which I'll write as 0.5, times K, which is our 150 newtons per meter, times X squared. So that's 0.1 meters squared, and we end up with 0.75 joules. So the work done on compressing the spring gives the spring 0.75 joules worth of potential energy. Let's talk about work done on a spring. So work done on a spring by stretching or compressing is positive. So from Hooke's law, we have the equation F is equal to K times X. So if we plot that on a graph, we have F in the y-axis, X on the x-axis, and we have this little triangle here. So the work is the area of the triangle. So the area of this triangle is work. So again, if we look at our diagram, we've got the force acting on the spring, the pulling the spring, stretching the spring, or compressing the spring if we were pushing on the spring in that direction. So let's look at our equation for area. So the area of a triangle is 1/2 base times height. So looking at that more specifically in terms of our graph here, we have 1/2 x times f. So the base is x, the height is f. And f is replaced by kx, which we have here. So our work becomes 1/2 kx squared, which is why work on a spring by stretching or compressing is always positive, because it doesn't matter whether you're stretching the spring, so your force is exerted in a positive direction, or you're compressing the spring, so your work is in the negative direction, because that deformation of the spring is squared, it's always going to be positive. Okay, so let's look at an example, another example. So we have a 5 kilogram block, compresses a spring with a spring constant of 1,000 newtons per meter by a distance of 0.5 meters. So what is the block's velocity after being released? Okay, so we have the mass of the block is 5 kilograms. The spring is compressed. So let's imagine a diagram here. So we have a spring, we have a block. So let's say that this is the original position of the spring, and this is the new compressed position. And so this distance here is 0.5 meters. And then we want to know, what is the velocity of the spring after it is released? So once it gets to that place, the block is going to travel in this direction. And it's going to have some velocity. We want to know what that is. Okay, so we have masses 5 kilograms, K is 1,000 newtons per meter, and the distance that the spring is compressed is 0.5 meters. Okay, so we're going to use conservation of energy to solve this problem. So we have, on the left side of our equation, we have initial kinetic energy plus initial spring energy, or potential energy. And on the right side, we have final kinetic energy plus our final spring potential. So to begin with, we have 0 kinetic energy, and we have only spring energy. And then on the other side of the equation, we don't have any spring potential energy because the spring has stretched out. It's no longer compressed, and we only have kinetic energy. So let's look at our spring potential. So remember, spring potential energy, UE, is equal to 1/2 K times X squared, and kinetic energy is equal to 1/2 M times V squared. So our UE naught is going to equal 1/2 times our K, which is 1,000 newtons per meter, times our X, which is 0.5. It's 0.5 meters squared. And that's equal to our kinetic energy, which is 1/2 our mass, which is 5 kilograms, times our velocity, which is what we're looking for, v squared. Okay, so on both sides of the equation, we have this 1/2. So we're going to delete out this 1/2, divide out the 1/2. So we have 0.5 squared, so that's 0.25 times 1,000 newtons per meter. So that gives us 200 newtons, and then per meter and times meter squared gives us 1 unit of meters. So newtons times meters equals 5 kilograms times v squared. So divide both sides by 5. No, that should be 250. Sorry, 250 newtons times meters equals 5 kilograms times v squared. So dividing by 5 kilograms, that gives us 50 meters squared per second squared. And that gives us equals v squared. So moving over here, so v then is going to equal 7.1 meters per second. So I'd like to look at these units real quick. So we have Newton meters and kilograms. So newtons are equal to kilogram meters per second squared. So when we divide by kilograms, we get rid of those kilograms. And so when we have Newton meters, that equals kilograms meters squared per second squared. So when we divide by kilograms, we get rid of the kilograms, we're left with meters squared per second squared is what we have here. And then we take the square root of that and we just get meters per second. So the velocity of the block after being released by the spring is 7.1 meters per second. Okay, let's look at example number 3. So we have a 10 kilogram block at a height of 2 meters, slides down a frictionless ramp and collides with a spring with stiffness 100 newtons per meter. How far will the block compress the spring? Okay, so we're going to use energy conservation again. So at the top of the ramp, we have potential energy, gravitational potential. And that's pretty much all we have. So at the bottom of the ramp, we have spring potential energy. So we have gravitational potential and spring potential. So gravitational potential, remember, is mgy, and spring potential is 1/2 kx squared. So we know our m is 10 kilograms, our g is 10 meters per second squared, and our y is this height of 2 meters. And then for gravitation, or for spring potential, we have our k of 100 newtons per meter, and our x is our question. We don't know how far the block will compress. So we have 10 kilograms times 10 meters per second squared, that's our g, times our height of 2 meters, and that's equal to 0.5 times 100 newtons per meter times x squared. Okay, so simplifying over here, we have 200 kilograms meters squared per second squared, and that's equal to 50 newtons per meter times x squared. Okay, so divide both sides by 50 newtons per meter, and that gives us 4 meters squared equals x squared. So that gives us an x that equals 2 meters. So the spring, once the block hits it here, the spring is going to be compressed. This x is going to equal 2 meters. Okay, so let's look at these units again. So we have kilograms meters per second squared, or kilograms meters squared per second squared, divided by 50 newtons per meter. Okay. So newtons are equal to kilograms meters per second squared. So if we divide by kilograms, so if we have kilograms meters squared per second squared, and we divide that by kilograms meters per second squared. So we have kilograms meters squared per second squared divided by, now we're dividing by newtons per meter. So we're dividing by kilograms meters per second squared per meter. So our kilograms meters per second squared takes out kilograms, one of our meters, and per second squared, and then this per meter at the bottom ends up coming back up and giving us another meter squared. So in the end here, we end up with meters squared, which is what we have here. 4 meters squared equals x squared. So when we take the square root of both sides, we end up with just a single unit of meters. Okay, and finally, example number 4. We have a 2 kilogram ball, sits on a frictionless table with a height of 1.5 meters and compresses a spring with a stiffness 200 newtons per meter, a distance of 0.5 meters. So we want to know what is the speed of the ball as it hits the ground. Okay, so we've got 3 different types of energy in this problem. So we have kinetic energy. So on top of the table, we have kinetic energy, initial kinetic energy plus initial gravitational potential energy plus initial spring potential energy. And that's going to equal our final kinetic energy plus our final spring or gravitational potential energy plus our final spring potential energy. So at the beginning, the ball has no velocity. So the ball has no kinetic energy. It does have potential energy because it is on top of the table. It has a height of 1.5 meters. It does have spring energy because it's compressed a spring a distance of 0.5 meters. And it does have, okay, so we have potential, gravitational potential and spring potential. Now, on the ground, right before it hits the ground, it does have kinetic energy because it has a speed, but it doesn't have a gravitational potential because it's just about to hit the ground. So we can say gravitational potential is 0, and it doesn't have spring potential anymore because the spring is no longer compressed. So the spring returns to its unstretched or its uncompressed state, which gives it 0 spring energy. Okay, so our gravitational potential energy is mgy. So our m is 2 kilograms. Our g is 10 meters per second squared. And our height, then, y, is 1.5 meters. We add to that our potential, our spring potential energy. So that's 1/2. So I'll call that 0.5 times k, which is 200 newtons per meter, times x, which is 0.5 meters squared. And that's equal to our kinetic energy right before we hit the ground. So that's 0.5 times our mass, which is 2 kilograms, times v squared, because we don't know v. Okay, so multiplying some things out, simplifying some numbers, we have 20 times 1.5, that gives us 30 kilogram meters squared per second squared. So then we have 0.5 times 200 newtons per meter times 0.5 squared, which is 0.25. So that gives us a total of 25 newtons is kilograms meters per second squared divided by meters. So that's kilograms per second squared, but we're multiplying by meters. So we have kilograms meters squared per second squared. So we have like units here. And then that's equal to 0.5 times 2. So that is equal to 1 kilogram times velocity squared. Okay, so adding everything on the left side, we have 55 kilograms meters squared per second squared equals 1 kilogram times v squared. So divide everything by a kilogram. We end up with 55 meters squared per second squared equals v squared. Take the square root of both sides, and we end up with a final velocity of 7.4 meters per second. So the speed of the ball as it hits the ground is 7.4 meters per second.